Swayam Prabha. Digital India. Educated India.
Okay, let's get started. So, welcome to the class, and what we will do is do a small recap of what we did yesterday, and then we will see how we can use the same approach for solving ordinary differential equations which are linear. Okay. So, we were looking at solving Ax equals b, and we are interested in the case where A is not self adjoint, where A is not equal to A transpose. Okay. What if A is not equal to A transpose? That is, A is not self adjoint, the adjoint is not equal to the original operator. Now, what we did yesterday was we actually did an example, okay, but now I will just put it in the form of a theoretical context so that the theory is clear. So, again A has, let us say, n eigenvalues and n eigenvectors. A transpose has again n lambdas, same lambdas, and these eigenvectors I am calling ui, these eigenvectors I am calling vj. Okay. I is just going from 1 through n, j goes from 1 through n. So, just to differentiate the eigenvectors I am giving a different notation. So, and the eigenvalues of A and A transpose are the same. So, the lambdas are kept the same, okay, and so, but these eigenvectors are ui, these eigenvectors are vj. Now, what we want to do is we represent x, the vector which we want to determine, because that also belongs to the same space. We use these eigenvectors as a basis, ui as a basis, and we write it as sigma ci ui. Now, the ui form the basis, okay. And b is written as sigma beta ui. Now, what we want to do is we want to find x so that it satisfies this equation Ax equals b, okay. So, what is Ax? A sigma ci ui, and this must be equal to b, which is sigma beta I ui. Because A is a linear operator, I can write this as sigma lambda, let me do it step by step, A ui equals sigma beta I ui, and this is sigma ci lambda I ui minus sigma beta I ui equal to 0, or sigma okay. Basically the same thing, it does not matter whether A is adjoint, self adjoint or not, okay. This part is the same. So, basically because the argument is now the ui's are independent, that means the coefficients have to be 0, okay, because the ui's are independent, we have Ci must be equal to beta I divided by lambda I. So, this is the same, Ci is beta I by lambda I is the same whether A is self adjoint or not, okay. It does not matter, okay. That is what I wanted to show. But what is important is the calculation of this beta I, that is different. So, lambda I you find the usual way, but the calculation of beta I is different because the ui is now done form an orthogonal set, okay. So, that is the only thing which you have to keep in mind. So, basically this concept of, so the lambdas, I have lambda 1, lambda 2. So, I have lambda 1, lambda 2 up to lambda n. Let me add one more lambda here. Corresponding to this, I have u1, u2, u3, un, and I have v1, v2, v3, vn. These are the eigenvectors of A, these are the eigenvectors of A transpose. Now, these two sets form are biorthogonal. What does this mean? This means u1 is perpendicular to v2, v3 up to vn, u2 is perpendicular to v1 and v3, u2 is not perpendicular to v2, okay. u1 is not perpendicular to one corresponding to same eigenvalue, these are not perpendicular. So, basically I am saying and it is perpendicular to the complex conjugate, okay. So, I am saying u1 Vj bar equals 0 for j equal to 2 onwards, or I can write inner product of ui with Vj bar equals 0 for I not equal to j, for all I not equal to j. If I is equal to j, it is non-zero, okay. So, u2 is perpendicular to v1, v3 etc. u3 is perpendicular to u1, v2, v4, okay. So, this you have to be clear about, perpendicular not to this but the complex conjugate of it. If these vectors are real, it does not matter, okay. And this is what we have to use, this biorthogonality is used for finding the beta I. So, when I write B as sigma beta I ui, I will take the inner product on both sides with Vj bar, okay. So, this is I going from 1 through n, take the inner product on both sides with Vj bar, and what do I get? Okay. Now, because of the biorthogonality property, this j will be some number, I should put this on top, okay. Supposing you take v1 bar, this will be j is 1, this will be 1, only 1 and u1 will contribute, all the other terms will be 0, okay. So, what I am saying is because of the biorthogonality property, only one term will contribute when I is equal to j, okay. So, only when I equal to j this is going to contribute. So, this is going to be written as Vj bar comma beta j uj, because everything else is 0, okay. And so, basically beta j turns out to be inner product of Vj bar with B divided by inner product of Vj bar with Uj. This is exactly what we did yesterday. Yesterday I did it with a specific example. I took a 2 by 2 matrix and I had only u1 v1 and u1 u2 v1 v2. Only thing is everything was real, so I did not have to do a complex conjugate. Okay. So, this is the theoretical framework by which we have extended how to solve Ax equals b to non self adjoint systems. Okay. Now, so I want to show how I can extend whatever we have done for x dot equals Ax. I am solving a system of linear equations now. Now, let me explain to you what is the meaning of x dot equal to Ax. It is like saying I have two differential, let us take a simple 2 dimensional case. X1 dot dot represents time derivative, okay, is of the form a11 x1 plus a12 x2. X2 dot is a21 x1 plus a22 x2. So, I have two equations which are coupled to each other and they are linear. Okay. This kind of a system we saw, for example, the batch reactor example when you had a first order reaction. Okay. All the reactions are first order, so the concentrations are going to depend upon, and there are many reactions going on. So, basically this could be concentration of one species, this could be concentration of another species, and you know, they are all reacting with each other. So, I have two linear equations. Of course, you can generalize it for n equations, but let us focus on two equations to give the idea. Okay. So, what I have done is I have taken these two equations. This is linear because the derivative and the x1, the dependent variables are all occurring to the first power. This is also occurring to the first power. Okay. These are, I will say, two coupled linear ordinary differential equations. They are coupled because x1 depends upon x2 and x2 depends upon x1. Okay. They are dependent on each other. The two variables, that is what I mean by coupling. If they are not dependent on each other, if x1 depends only on x1 and x2 depends only on x2, then they are not coupled, but now they are coupled and they are linear. Okay. And there is only one independent variable, which is time. So, it is an ordinary differential equation. So, equation of this kind I can write x as x1 x2. Okay. That is my vector again, but now x1 and x2 are functions of time. Okay. This is a function of time and this is also a function of time. And I can write this as d dt of x1 x2 equals a, which is ax x2, and a, remember, is a11 a12 a21 a22. Okay. So, that is what I have done. I have taken this equations and I have recast it in a vectorial notation. System of two equations linear, because they are linear I am able to write it in the matrix form here. Okay. That is how I get this. In order to solve this, because in ordinary differential equation you will get some arbitrary constants of integration, you need to specify some initial condition. Okay. So, at time t equal to 0, we have to specify x1 is equal to x1 naught, x equal to x naught, sorry, x equal to x naught. What this means is x1 is equal to x1 0, x2 is equal to x2 0. So, basically at time t equal to 0, I need to know the value of both the variables x1 and x2, okay, only then I can solve, that is the initial condition, okay. But now because of two variables, I need to specify both at t equal to 0, x1 is some value which is known to me, x2 is some value which is known to me. So, this x1 0, x2 0 is known to me, okay. This vector is x0. So, x0 is x10, x20, okay. Now, what we want to do is, we want to write x of t as summation in terms of ui, I equals 1 through n. Again, I am writing my vectors in terms of my eigen basis, eigen vectors which I am using as a basis, okay. But these vectors now are dependent on time, and the eigen vectors are not dependent on time, because eigen vectors are coming from A, which is constant. So, where do I absorb the time dependency? I need to absorb the time dependency in the constant, okay. So, you understand that the ui, the eigen vectors, they are coming from a matrix which has constant coefficients. So, eigen vectors are not going to be dependent on time, okay, they are just some vectors, but your actual solution is dependent on time. So, the constant I am saying varies with time. So, this is the ui's are independent of t, okay. So, what is x dot now? I differentiate both sides with respect. So, is this clear? I have just written my vector in terms of the eigen basis, absorb the time dependency in the coefficients. Now, the time derivative is just I will differentiate both sides with respect to time, and this does not depend on time. So, this is nothing but I is equal to 1 to n Ci dot of t ui. Just differentiate. And what about Ax? That is going to be A operated on Ci of t ui, I is equal to 1 through n. Again I can take the A inside the summation. Ci is not a vector, Ci is just some scalar which is a function of time. I can write this as sigma A Ci ui, Ci A ui, okay. Which is equal to sigma Ci of t A ui same thing what we did earlier. When I am operating by A, I just say this is equal to this, okay. So, now x dot equal to Ax. So, I need to find the x, okay. I need to find the x, which means I need to find the Ci's. If I can find the Ci, I can find the x, okay. My job of trying to find the x is converted to finding the Ci. So, I need to find the Ci, and therefore, I am just going to find the Ci. So, this equation is satisfied, okay. So, x dot is sigma Ci dot ui n equals sigma lambda I Ci of t ui, I is equal to 1 through n. And I will again group these two to one side. equal to 0. So, you can see I am using the same argument again and again. So, again UIs are independent. So, at every time instant the coefficients have to be 0, okay, and therefore, we say that Ci dot of t must be equal to lambda I Ci of t for all I for all t. And Ci, remember, is just a coefficient, is a scalar. Ci is just not scalar, but only thing is a function of time now. Okay. So, I have C1 of t, C2 of t, C3 of t. So, all of this can be integrated, like this is just a first order ordinary differential equation. Okay. So, what is the integration of this? d dt of Ci equals lambda I Ci, which means Ci of t is Ci of 0 e power lambda I t. Okay. That is basically what we got now. So, Ci of t is going to be of this form, which means my x of t is going to be of the form Ci of t e power ui. This is the form we assumed for earlier, what I erased. So, this is going to be of the form sigma Ci of 0 e power lambda I t ui. Okay. So, I calculated Ci of t and I substituted it here, and I am getting this as I is equal to 1 through n, 1 through n, yeah. Our job now, I still have not found the solution. What is the Ci of 0? It is an arbitrary constant of integration which comes, right. When you integrate this, you will get a constant of integration. What is the Ci of 0? This is the constant of integration. Okay, when you integrate it, basically at time t equal to 0, you put t equal to 0, Ci of 0 will be equal to Ci of 0. What is the value of Ci at time t equal to 0? Because I am having one differential equation. So, now I am yet to find out the Ci of 0. If I know Ci of 0, I have the solution, because these are the eigen vectors of A. E power lambda I t is known because the eigen values are known. I do not know Ci of 0. How do I find Ci of 0? I have to use the initial condition. Okay. I need to use the initial condition at time t equal to 0. What is the value? Okay. Find use at t equal to 0, x is equal to x naught. Okay. This is my initial condition which is given to me, otherwise I can't solve the problem. So, now if I put t equal to 0, this becomes 1, and I have x naught equals sigma Ci of 0 ui, I is equal to 1 through n. So, this vector here is known to me. It is something like the b I had in the earlier problem, Ax equals b, b was known. Okay. So, this vector is known because I know the initial condition, and now I can do whatever I did. This is of course a constant, because this Ci at time t equal to 0, this is a constant, this is like my beta I, and this is like my ui. Okay. So, I am saying this is analogous to b equals sigma beta I ui in Ax equals b. I mean, the summation of ui is there. This was unknown, beta I did not know, I had to find out. I need to find out Ci of 0, and this is given, this is like my b. So, I just wanted you to, now you know this, you can find out what the CI zeros are. If A is self-adjoint, you will use the orthogonality property. If A is not self-adjoint, use the bi-orthogonality property, that is all. And you can find out CI of 0, then you can substitute it back inside and you have the solution. If A is self-adjoint, the UIs are orthogonal, and therefore CI of 0 will be inner product of x naught with ui divided by inner product of ui with ui. You will take the inner product of both sides with ui, okay. You will take the inner product of both sides with ui. If it is orthogonal, everything else will be 0, only one will contribute, okay. So, that is what I am getting. And if A is not self-adjoint, then you use the bi-orthogonality which we did earlier, okay. You will find CI of 0 is inner product of Vi bar with x naught divided by inner product of Vi bar with ui. Okay. So, this is basically what you have, okay. So, I mean this is exactly what we did for Ax equals b, and you need to understand, so b I have x0, okay, and I have why am I putting it at the subscript, sorry man, I need to, all these vectors have to have upper. So, superscript, okay, because there is ith vector is superscript I, that is what I said I will do, okay, so superscript I. Yeah. So, my job, I just extended whatever we have done for Ax equals b. The time dependency I absorbed it in my constant Ci. I wanted to make sure my equation is satisfied. My Ci has to be chosen so that the equation is satisfied. So, I did all of that and I got this equation. This unknown Ci of 0 I get by using the initial condition like he says, and this becomes like b which is known to me, and then it is finding it using orthogonality or bi-orthogonality. Okay. So, that is what we have done. Now, I want to tell you that this is something which you are possibly have seen in a different form earlier in one of your calculus courses, okay. So, I just want to make that connection before we proceed. So, this is similar to what you have seen before. Okay, I put a question mark because I don't want somebody to tell me he has not seen it before. So, if I have this matrix A, A11, A12, A21, A22, okay. I want to find the eigenvalues of this matrix. How will you go about finding the eigenvalues of this matrix? The lambdas come from the determinant of A11 minus lambda A12 A21 A22 minus lambda equal to 0. Okay. Earlier you did the problem when you actually had numbers, now I am just putting in terms of coefficients. It could be anything, it could be 1, 3, 4, 5, whatever. What is this? You can expand this. Okay, that is the determinant. This multiplied by this minus this multiplied by that, you expand this out, you get lambda squared minus A11 plus A22 lambda plus A11 A22 minus A12 A21 equal to 0. Okay. So, that is just simple this thing. What is this? This is nothing but the determinant of A, and this is nothing but the trace of A. Okay. So, I want you to understand that at least for a 2-dimensional problem with only 2 vectors, when your eigenvalues come from a quadratic, they are the eigenvalues are the roots of this quadratic equation. Okay. Now, so the lambdas are the roots of this equation, you can write it down. I want to go back to this thing here, x1 dot equals a11 x1 plus a12 x2, x2 dot equals I have just written this x dot equals ax in the full form, each row. Now, instead of having 2 equations in 2 unknowns, okay, I have 2 equations, one for x1, one for x2. I want to see if I can write it as 1 equation in 1 unknown. That is, I have to eliminate x2. Okay, I want to eliminate x2 and get an is it possible to do that? So, I am going to differentiate this first equation with time. So, differentiate this with respect to time, I get x1 double dot equals a11 x1 dot plus a12 x2 dot, that is differentiating with respect to time, equation 1. Okay. And for x2 dot I can substitute it back from this equation. Okay. So, a11 x1 dot plus a12, what is x2 dot? A21 x1 plus a22 x2. Okay. What have I done? I have just taken this equation for x2 dot and substituted it here, and this becomes a11 x1 dot plus a12 a21 x1 plus a12 a22 x2. A12 x2 dot, a12 x2 dot is a21 x1 plus a22 x2. Yeah, must be right. Let us move on. So, I have x1, 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 but I still have an x2 here. I do not like, because I said I want everything in terms of x1. So, when we come back here and write, use this first equation to write x2 in terms of x1 dot and x1. Okay. So, a12 x2, a12 x2 is x1 dot minus a11 x1. So, I have dot plus A12 A21 x1, okay, and this I will write as A22. What is A12 x2? X1 dot okay minus A11 x1. Okay. So, I am going to write all of this now as now basically this whole equation is in terms of x1, x1 double dot, everything is in terms of x1. I will manage to eliminate x2. That was my objective, right? Two equations, two unknowns, get one equation, one unknown. And I am going to write this as x1 double dot equals A11 x1 dot A22 plus A22 x1 dot plus A12 A21 minus A11 A22 x1 equal to 0. Okay, I am going to bring everything to one side, put right hand side as 0. It is just a manipulation I am doing, you can do it, okay. I am quite happy with how this final equation now. Now, these are equations which you have solved because these are linear equations, second order linear equations with constant coefficients, because A11, A12 are all constant coefficients, okay. How do you solve this? Yeah, so you seek a solution in the form of e power mt. I mean, this is what you have done, okay, because this is a second order linear equation with constant coefficients. Second order linear, but everything is to the power 1 and these coefficients are constant. And how do you seek the solution? X1 of t is e power mt, something like this, okay. This is what you have done before, or should have done before. So, what you do is you end up substituting this has to satisfy this, you find m, so that this equation is satisfied, okay. When you substitute this here, what do you get? M squared minus A11 plus A22 times m. I mean, maybe I should do this properly. So, you differentiate this 2 times, you get m squared minus differentiate this once, you get plus zero. E power mt cannot be 0, that means you are looking at the 0 solution, okay. So, you want this equation to be satisfied and e power mt is not 0. So, e power mt is not 0, this implies therefore, m squared minus A11 plus A22 m plus A11 A22 minus A12 A21 equals 0. So, m is the root of a quadratic, okay, and this is exactly the trace of A, this is the determinant of A. So, m squared minus trace of A times m plus the determinant of A equals 0. So, this m is nothing but the eigenvalues of the matrix A. When you write this second, if you did went reverse from matrix, I got the second order equation. From second order equation, if I wrote two first order equations, I would have gotten the matrix. Okay. So, point I am making here is this m is the same as the eigenvalues of A. Okay. And this is and then you do your usual stuff. So, I was only trying to connect what we have already done before with what we are doing now in the vector notation. In the vector notation, I directly got the eigenvalues. I have said I am doing it in the form of an eigen basis. Okay. So, I got the solution. What you did is, I mean, you did not worry about vector and all that, you were given a second order equation, you solved it. I think the point is, if I have two first order equations with constant coefficients, I can write it as a second order equation. Okay. So, this is a thing. So, basically second order linear ODE with constant coefficients is I should have written it the other way, anyway, is obtained from two first order coupled ODEs. Now, let me write. So, if I have n coupled linear ODEs, and I can do this elimination, I will get an nth order equation in a single variable. Okay. So, if I have n linear coupled ODEs with constant coefficients, we can write it as an nth order equation in one variable. Okay. So, like he just said, if you have a second order equation, constant coefficients, you seek the solution forms of e power mt. The m turns out to be a quadratic, and that is the equivalent of an eigenvalue. That is the reason I made that eigenvalues of A. That is governed by the same equations as what we are getting now. Okay. And if you have an nth order equation, then you will have if you have n coupled linear ODEs, you can do this elimination and you will get an nth order equation for one variable. Like I got two equations, I got one equation which is second order in one variable. For n equations, I get nth order in one variable. Okay. So, basically, I mean, I think if you understand this, you will possibly be able to appreciate these connections. So, what you have done earlier is what I am doing, but I am just putting it in a different perspective, different form. Okay. I am writing everything in terms of a vectorial form, that is all. And yeah, so as far as solving problems is concerned, I think you are all experts in solving problems. Now, you can use bi-orthogonality and orthogonality and you can solve. So, we will give some problems for you to work on and get comfortable. Thank you.